In this video, we are going to look at beta oxidation of fatty acids. That is the process and the mechanism involved in the reaction, and most importantly, how to calculate the net ATP yield from beta oxidation of fatty acids. So let's begin. Now, basically, beta oxidation, as the name implies, is the oxidation of the fatty acid on the beta carbon. So let's say we have a long chain fatty acid, which looks like this. So we have a long chain fatty acid, which is basically a carboxylic acid chain. This carbon is the alpha carbon or the fatty acid. Then this carbon is the beta carbon or the fatty acid. Now the process tends to add oxygen to the beta carbon and at the end cleaves this portion of the fatty acid to form what we call an acetyl-CoA. So we call it beta oxidation because the process involves oxidation on the beta carbon of the fatty acid. Now this process occurs normally when there is no glucose in the living system, or let's say when there's a limited amount of glucose in the living system. The body uses fatty acids stored in the adipose tissue to generate enough energy for use. Or let's say in a state of diabetes or a long starving state, there's going to be an onset of beta oxidation fatty acid to produce enormous amount of acetyl-CoA, which we tend to produce ATP from it. Now the process occurs from the cytoplasm. It starts from the cytoplasm and occurs most importantly in the mitochondrial matrix. So it begins in the cytoplasm and occurs importantly in the mitochondrial matrix. So you're going to look at how it begins in the cytoplasm and ends and occurs proper in the mitochondrial matrix. So as you said earlier, the long chain fatty acid tends to break apart to acetyl-CoA units. So this compound is a complex with 2 carbons. And if you have a long chain fatty acid, it means it breaks into fragments of 2. So let's say if you have, let's say, 10 carbon carboxylic acid or fatty acid, it can cleave into, let's say, 5 residues of acetyl-CoA. So for a long chain fatty acid, we generate all the 2 fragments into acetyl-CoA if only it is an even chain carbon, with exceptions. If it is an even chain fatty acid, then we are going to have all the carbons into 2 fragments, of which each of them will form acetyl-CoA in the living system. Now the process basically involves a series of steps. It involves the first step called activation. We have transportation and the beta oxidation proper, which occurs in the mitochondrial matrix. So we are just going to have overview of these processes. Then we delve into the proper calculation of ATP yield from beta oxidation. So as shown here, this is how maybe the mitochondria look like. So when you take every living cell, it has the cytoplasm and the mitochondria. So in the cytoplasm is where the transport and activation begin. So let's look at how beta oxidation begins with what? Activation and transportation. Now let's say this is our cell. If we are assuming this side of the cell is the cytoplasm, and these 2 layers are the 2 layers of the mitochondria. So bear in mind, mitochondria has 2 layers. It has an outer membrane which is permeable to almost all substances, and an inner membrane which is impermeable but has integrated transporters that enable substance to move in and out of the mitochondria. So it has 2 transporters or 2 membranes, the outer membrane and the inner membrane. The outer one is permeable to almost all substances, but the inner one is not permeable, but it is very selective because it has an embedded transporters that enables transport of substances in and out of the mitochondrial matrix. So shown here is the cytoplasm. This side is the intermembrane space, the space between the inner membrane and the outer membrane. And here we assume here is the mitochondrial matrix where the fluid or the beta oxidation proper occurs. Now look at something. We have fatty acid synthesis occurring in the cytoplasm. We saw it in our earlier videos that fatty acid synthesis occurs in the cytoplasm and it uses acetyl-CoA molecules for the synthesis. Now the beta oxidation is the reverse or the inverse of the fatty acid synthesis, which cleaves all the fatty acids synthesized in the cytoplasm into fragments of acetyl-CoA. It means at any point in time, we are going to have the fatty acids in the cytoplasm, then more of the acetyl-CoA in the mitochondrial matrix, because the beta oxidation which cleaves the fatty acid into acetyl-CoA occurs proper in the mitochondrial matrix, except acetyl-CoA produced from glycolysis. So if you have, say, fatty acids free in the cytoplasm, the first step is the activation. Now the activation is not anything. What the body does is it will first add a CoA enzyme to the fatty acid to form an acyl CoA. So that's the activation step. The first activation step is the body adds a CoA enzyme to the fatty acid to form acyl CoA. And the enzyme involved in there is called an acyl CoA synthetase, which uses ATP molecule for the activation. So I think about 2 ATPs are used for the activation of the fatty acid, where it adds a CoA enzyme to the fatty acid to form acyl CoA. So that's how it goes. So that's the first activation. The next thing is there is a transporter for fatty acid or for the fatty acyl CoA called carnitine. So the carnitine is the transporter for the fatty acyl CoA that is in the cytoplasm. Then in the intermembrane space, there is a protein called translocate that opens a channel for the translocase open a channel in the inner mitochondrial membrane for the activation of the acyl carnitine to move out. Now, after the activation, that is the addition of the CoA enzyme to the fatty acid to form the acyl CoA, another enzyme called CAT1, which is called carnitine acyl transferase 1, carnitine acyl transferase 1. This enzyme would transfer the acyl portion of the acyl CoA to the carnitine to form an acyl carnitine. So this one occurs in the intermembrane space. After the activation, which uses 2 ATP, the carnitine acyl transferase 1 will transfer the acyl group of the acyl CoA. Bear in mind, the acyl CoA is a long-chain fatty acid esterified through the CoA enzyme. So the acyl CoA, the carnitine acyl transferase 1 will remove the acyl portion of the acyl CoA to the carnitine transporter or the carnitine shuttle to form acyl carnitine. Now the acyl carnitine is a mark that the translocate protein can allow to move into the mitochondrial matrix. So when the carnitine acyl transferase 1 transfer the acyl group from the acyl CoA to the carnitine to form acyl carnitine, the next step is that the acyl carnitine, which is the complex of the fatty acid, the acyl portion of the fatty acid, then the carnitine shuttle will now move into the mitochondrial matrix through the protein complex called the translocase. So the translocase here is the protein channel that allows the acyl carnitine to move into the mitochondrial matrix. So the fatty acid reaches the mitochondrial matrix in the form of acyl carnitine. Now, when it gets in the mitochondrial matrix in the form of acyl carnitine, the next step is the CAT2, which is the opposite of the CAT1, or perform the same function, but they are found in different environments. Carnitine acyl transferase 2. This one will remove the acyl portion of the acyl carnitine and add it to the CoA and form acyl CoA back. So bear in mind, we did activation in the cytoplasm from acyl CoA. So if you get in the mitochondrial matrix, you have to get back the acyl CoA. So the acyl CoA is formed by the transfer of the acyl group of the carnitine acyl carnitine formed by the carnitine acyl transferase 1 to form the acyl CoA. Now, when you reach the transport, when you reach here, that is why I have the fatty acid long chain esterified CoA enzyme. Now, from here, the beta oxidation will occur. We are going to have this series of steps so we can break down the long chain fatty acids into 2 fragments of carbon to form acyl CoA. Now, let's look at the next step. So, shown here is how basically the transport occurs. So, we have what we call a triacyl glycerol, TAG, which is the form of fat, or the storage form of fat in the adipose tissue. So it is made of a glycerol backbone esterified with 3 fatty acids. So if the body is in need of fatty acid, or for this need for beta oxidation, there is going to be a lipolysis where the ester linkage between the glycerol and the fatty acids will break apart to relieve the free fatty acids. That's what we call lipolysis. When there's lipolysis, we are going to have free fatty acids in the system. Fatty acids in the system. So the next step, which is by the acyl activation, is the addition of the fatty acid to the CoA enzyme. So that's by the acyl CoA synthesis. Here is where there is a use of ATP. About 2 ATP molecules are invested in the activation state. So when we add the CoA enzyme to the fatty acid to form the fatty acyl CoA, as we said earlier, the carnitine will now come and link up the acyl group, so we form fatty acyl carnitine. This one is what is catalyzed by the CAT1, carnitine acyl transferase 1, that transfers the fatty acid or the acyl portion of the fatty acyl CoA to the carnitine to form fatty acyl carnitine in the intermembrane space. The next thing is this transporter, which is having a complex with the fatty acid, will now move through the protein complex in the mitochondria, the inner mitochondrial membrane, as fatty acyl carnitine and gets into the mitochondrial matrix. So when again the mitochondrial matrix, that's where the CAT2 will now come into function to remove the acyl portion of the fatty acyl carnitine and add it once again to the CoA enzyme to form the fatty acyl CoA. Now this carnitine can now move back to the cytoplasm to pick another fatty acid. So the carnitine here is a transporter, and the road it passes through is through the protein called the translocase, which is embedded in the inner mitochondrial membrane. So after activation and transport, now there is going to be the beta oxidation proper. So 4 steps are involved in the beta oxidation proper. This one basically occurs in the mitochondrial matrix. We have oxidation, we have hydration, we have oxidation again, and dialysis. So let's look at the proper beta oxidation, where we believe that we transported our fatty acids from the cytoplasm to the mitochondrial matrix. So let's look at beta oxidation proper. Now here is the fatty acyl carnitine, which comes into the mitochondrial matrix. The first reaction of the beta oxidation proper, the one we said, is the oxidation. Now the oxidation here is more of a dehydrogenation process, where we take 2 hydrogens from the alpha carbon, one from the alpha carbon and the beta carbon. So for the first step, catalyzed by the acyl CoA dehydrogenase, it uses the cofactor FAD. Now here there is a release of hydrogen, one from the alpha carbon and one from the beta carbon. So we can have a double bond between the alpha carbon and the beta carbon, as shown here. This is a double bond that will be formed between the alpha carbon and the beta carbon. Now these 2 hydrogens will be transported or transferred to the FADH to FAD to form the FADH. Bear in mind, or just remember that in our previous video we said the FADH2 is an electron carrier that can be converted to ATP in the electron transport chain. So in the ETC, the FADH can give us an equivalent of 2 ATP molecules. That's the first step of the beta oxidation proper. The next step is what we call hydration. Now for the hydration, now we have a double bond between the alpha carbon and the beta carbon. This hydration is just addition of water molecules, which has a hydroxy group, OH, and a hydrogen. So this water was split into 2, OH and H. Then the OH portion of the water will now add to the beta carbon. Then the H will now add to the alpha carbon. So it's going to be an oxidation because of the added oxygen. Catalyzed by the enol CoA hydratase, we have water being added to the compound with a double bond. And that double bond will break apart and we add hydrogen and OH from water. The next step is also another oxygenation, or let's say dehydrogenation or oxidation. In the next oxidation process, what happens is we are going to pick the oxygen or the hydrogen on the oxygen and the other hydrogen on the same beta carbon, and these 2 hydrogens will be added to NAD plus to form NADH. So as seen here, we add these 2 hydrogens to add to NAD plus to form NADH. So when we have this, there's going to be addition of these 2 hydrogens to NAD plus to form NADH. So when we have that, there's going to be a formation of a ketone on the beta carbon. So we have an oxidation occurring. That's why we call it beta oxidation, because we add a beta, let's say oxygen, to the beta carbon of the fatty acid. The next step is what your cleavage. Catalyzed by a thiolase, the 2 carbon fragments, what is the carbonyl carbon and the alpha carbon, will be cleaved. When they cleave, these 2 form acetyl CoA molecule. Then the remaining acyl group will undergo the same sequence again, where this one can now become the carbonyl carbon. This one can become the alpha carbon. Then the next beta carbon will go through these same processes. So we are going to generate what? We generate equivalent amount of ATPs, or let's say acetyl CoAs. So in all the process, we are going to have cyclic process where we are going to have one NADH produced at one step, then one FADH produced. So for each cycle of beta oxidation, we are going to produce one NADH and one FADH2. They are produced in the oxidation steps of the beta oxidation in the mitochondrial matrix. So let's look at what happens is these two molecules will now run through the electron transport chain to produce equivalent ATPs. Bear in mind, we said the NADH can give us an equivalent of 2 ATPs. Then the FADH2 can give us equivalent of, this one can give us 3 ATPs. Then the FADH2 can give us equivalent of 2 ATPs. Now the produced acetyl CoA from the beta oxidation will now enter the Krebs cycle and also produce equivalent amount of NADH. So if you have just one acetyl CoA from beta oxidation or even from glucose, it will blend with oxaloacetate to form citrate. And this one in the Krebs cycle, this one acetyl CoA can give us an equivalent of 3 NADH, one at this step, one at this step, one at this step, then also one FADH2. So you have one FADH2, then we have one GTP. So GTP is an energy equivalent of ATP. So since we said one NADH gives us 3, if we have 3 NADH, we're going to get an equivalent of 9 ATPs. Now one FADH to give us equivalent of 2 ATPs. Then one GTP is equivalent to 1 ATP. It means that for a run of one acetyl CoA in the Krebs cycle, we are going to generate an equivalent of 12 ATPs. 9 from the NADH in the Krebs cycle, 2 from the FADH2 in the Krebs cycle, and 1 which is an equivalent of the GTP. Now let's look at calculation of the net ATP produced from beta oxidation of fatty acids, the energetics involved in what beta oxidation. So for so far, what we have learned so far, for us to have a beta oxidation, you have to get a particular number of rounds so we can clip all the fatty acids into 2 carbon fragments called acetyl CoA. So let's say I have a fatty acid with, let's say, 10 carbons. The fatty acid with 10 carbons. Now what happens is, when this 10 carbon fatty acid goes through beta oxidation, it is going to give me an equivalent of 5 acetyl CoA molecules. So we are going to have 5 acetyl CoA molecules in the beta oxidation proper. Now for me to have this one divided into 5 acetyl CoAs, I'll go through series of rounds. So I'll go to the first cycle where I will get 2, then I'll leave with what, 8. I'll go to the second one where this one will now split into another, say, 2, and here will be left with what, 6. I'll go next, then I will have now here 6, then I will have here what, 4. I'll go to the next cycle and I will have here what, 8, and I'll get here what, 2. So for me to divide the 5 carbon or say 10 carbon fatty acid into 2 carbon fragments, I'll first cleave and have 8 the first round. I'll cleave the next one and get remained with 6. I'll cleave the next one and get remained with what, 4. Then cleave the next one and get remained with 2. That means that for a 10 carbon unit, if I want to divide it into 2 carbon fragment acetyl CoA, I'm going to go through what we call 4 cycles. The first cycle is this. The next cycle is this one. The next cycle is this. And the last cycle give me what? That. Let's say I have 14 carbon fatty acid. If I go the first cycle, I'll get remains with what? 12. If I go the second cycle, I'll get remains with 10. If I go the next cycle, I'll get remains with 8. If I go the next cycle, I'll get, which is the fourth cycle, I'll get remains with 6. If I go the next cycle, is the fifth cycle, I'll get remains with 4. Then if I go the last cycle, I'll get remains with what? 2. That means for me to divide a 14 carbon fatty acid into 2 carbon acetyl-CoA residues, I have to go through what? 6 cycles. Now if it is 10, I'll go through what? 4 cycles. So how do you find the number of cycles for a particular fatty acid in beta oxidation? When you are being given any fatty acids and you want the number of cycles that a fatty acid will undergo, we use this formula. You are going to have the number of carbons in the fatty acid divided by 2, then minus 1. So you have the number of fatty acids, carbons in the fatty acid divided by 2 minus 1. This one is if you want to find the number of cycles of a particular even chain fatty acid. So let's say if I have 14 here, then I'll have 14 carbons divided by 2 minus 1, which is what? So you see it's going to be 7 minus 1, which is what? 6. So it means for a 14 carbon fatty acid, I'll go through 6 rounds or 6 cycles before I can divide it into 2 carbon in its acetyl-CoA. In the case of the 10 fragment, I'm going to have 10 over 2 minus 1. So I'm going to have 5 minus 1, which is 4 cycles. 4 cycles. That will give me the number of, let's say, that will give me the number of cycles I will go to break down the fatty acid into 2 carbon fragment units acetyl-CoA. Try this. If you say that you have 26 carbon chain, the number of cycles for the 26 is going to be 26 over 2 minus 1. So which is equal to, I'll have 26 over 2, which is 12. Sorry, 13. Then minus 1 will give me what? 12. Now there's a trick here. If you have been given the even chain fatty acid, the number of cycles, you use this formula. That is the carbon unit divided by 2 minus 1. That's one the number of cycles in the fatty acid for beta oxidation. Now for you to get the number of acetyl-CoAs, it is just very simple. Just divide the number of carbons in the fatty acid by 2. So the number of acetyl-CoAs, so the number of the acetyl-CoAs, that one is given by the formula, the carbon number divided by 2. That's the number of acetyl-CoAs in the compound or in that can be produced from the fatty acid. Then the number of cycles, so the number of the cycles, that's where we have the carbon over 2 minus 1. So bear in mind, always the number of acetyl-CoAs is always 1 more than the number of cycles. That is to say, if you have, let's say, 16 carbon fatty acid, you are going to produce 8 acetyl-CoAs. Therefore, the number of cycles is going to be 7. If I have a 20 chain fatty acid, the number of acetyl-CoAs in that 20 is going to be 10. Then the number of rounds or the cycle is going to be 10 minus 1, which is 9. So the number of rounds for a fatty acid is always 1 less than the number of acetyl-CoAs. Bear in mind. Now let's do calculations involved in that. So far, per what we did so far, we said in Krebs cycle, we are going to generate an equivalent of 12 ATPs. And also for each cycle, we are going to produce what? 5 ATPs. So we are going to have 5 ATPs for each cycle. This 5 comes from 1 NADH produced, then 1 FADH2. These ones are produced in each cycle. Now the NADH here gives us 3 and this one gives us 2. So the addition for each one is what? 5. Then in the Krebs cycle, we are going to have 3 NADs formed, giving me 9 ATPs, 1 FADH here, giving me 2 ATPs, and 1 GTP, which is ATP equivalent. So the number of ATPs for each acetyl CoA is 12. Now let's see how we can get the ATP produced for each cycle or for each fatty acid. Let's say I have a fatty acid which is made of 14 carbons. Then I'm being asked to find the number of ATPs that can be produced from the complete oxidation of this fatty acid. This fatty acid, of course, will give me an equivalent of 7 acetyl CoAs. So we have 7 acetyl CoAs. The number of cycles for the 7 acetyl CoA is going to be 6 by what we have learned so far. So we have 6 cycles that can give me the 7 acetyl CoAs. So each cycle we said can give us 1 cycle is an equivalent to 5 ATPs. Each cycle gives us 5 ATPs. Therefore, the 6th cycle for the carbon 14 will give us 6 times 5 number of ATPs, which is equivalent to 30 ATPs. So for the cycles alone, I'm going to form circle ATPs from the cycles. Once again, we said each acetyl CoA goes through the Krebs cycle to give us an equivalent of what? So 1 acetyl CoA gives us an equivalent of 12 ATPs in the Krebs cycle. So if we have 7 acetyl CoAs, we are going to have 7 times 12 number of ATPs formed. If 1 acetyl CoA gives you 12, then 7 will give us 7 times 12. So the 7 times 12 is the number of ATPs which can be formed for each ion for the 7 acetyl CoA, which is 84 ATPs. So in total, the number of ATPs for the cycles and the acetyl CoA is going to be 30 plus 84. So then we add this. Now we said earlier that in the process we are going to use 2 ATPs for activation. So we are going to have 2 ATPs used for activation, that you have to subtract that 2 ATP from it. So you're going to have -2. So this -2 is the one we use for activation. That is going to give us an equivalent of 112 ATPs. So for complete oxidation of myristic acid, which is 14 carbon fatty acid, I'm going to get an equivalent of 112 number of ATPs. Let's try next one. Let's say we have a stearic acid. So we have a stearic acid, and we are being asked to find the number of ATPs from this fatty acid. Stearic acid is 18 carbon fatty acid, therefore can give me an equivalent of 9 acetyl CoAs. The number of rounds will always be 1 less than the number of acetyl CoAs. So I'm going to have 8 rounds or cycles. So simple. The number of ATPs is going to be this. I'm going to have first the 9 acetyl CoAs. Each one will give me 12. So I'm going to have 9 times 12 number of ATPs plus the cycles, which is 8, and each cycle gives me 5. So I'm going to have 8 times 5 number of ATPs. Then minus my 2, which I use for the activation. Therefore, I'm going to have, so I have 9 times 12, which is 114. Then plus 8 times 5, which is 40. Then minus 2. So I'm going to have 114 plus 40, then minus 2, which is going to give me an equivalent of 152 ATPs. 152 ATPs. That's so interesting. So we have simple way of calculating the number of ATPs. This is for an even chain fatty acid. If you have an odd chain fatty acid or even fatty acid with unsaturations, there's going to be slight differences. Watch out for the next video. We're going to look at how we can calculate the number of ATPs for an odd chain fatty acid and fatty acids with unsaturation. So try this once and drop your answer at the comment section. If I have a fatty acid made of 26 carbons, what is the total number of ATPs formed for this fatty acid? So try this and drop your answer at the comment section. If I have a fatty acid made of, let's say, 32 number of carbons, how many ATPs can be formed from this fatty acid? So try this once and drop your answer at the comment section and let's see. Thanks for watching.